Welcome, dear friends. In this lecture, we would be studying the second law of thermodynamics, a very interesting concept in thermodynamics. The objective is to discuss why the need of second law of thermodynamics to explore thermodynamics is necessary. In short, what the first law doesn't say, what are the limitations of the first law of thermodynamics, and why do we require the two statements of second law of thermodynamics to understand the engineering world from the thermodynamic perspective. So we would be discussing the limitations of the first law of thermodynamics, and we would be discussing the two statements of second law of thermodynamics. One is the Kelvin Planck statement, and other is the Claudius statement. So the outcome of the lecture, which is expected, is that you get a clear understanding of the second law of thermodynamics and appreciate its relevance. Uh, First law of thermodynamics, instead of mugging up the statement, if you look at it conceptually, first law of thermodynamics is simply an energy balance. It means that it tells us to account for the energy inflows and energy outflows. For example, if you look at this, the first picture of a potato, what you see is that this potato is a system, and the remaining thing which is surrounding it can be called as a surrounding. So potato becomes a thermodynamic system. And if you look at the energy flows, what you find is that there is a energy flow in the form of heat transfer from the surroundings into the system. So what happens is, because of this, if you look at it from the first law of thermodynamics, you know that the first law of thermodynamics mathematical statement for a closed system is Q is equal to delta E plus W. Now in this case, there is no W. W is equal to 0. So Q will go in increasing the internal energy. So Q is equal to delta E. So that is the reason why you find that delta E is also equal to 5 kilojoules. Okay, so that is a very interesting application of first law of thermodynamics, where you know what would happen to the internal energy of a potato when you are heating it by, let us say, 5 kilojoules. So when you are heating a potato and supplying a heat equal to 5 kilojoules, its internal energy would increase by 5 kilojoules, and that is nothing but the application of first law of thermodynamics. Look at this second case as an application of first law of thermodynamics. What you find is that there is a heat flow in, and also there is some heat loss. So you can imagine that there is some pressure cooker, for example, and you are keeping this pressure cooker on a burner, as a result of which there is some heat transfer via the burner of the gas into the pressure cooker. And because the pressure cooker is hot, so it would also reject certain heat. There would be heat loss from the pressure cooker to the surrounding. So let us say that you are supplying around 15 kilojoules of heat to a pressure cooker, and about 3 kilojoules of heat is being lost to the surrounding. Okay, so what would be the net change of internal energy? So again, by applying the first law of thermodynamics, Q is equal to delta E plus W, you can find out that the net change of internal energy is equal to net heat transfer, which is nothing but 12 kilojoules, 15 minus 3, which is 12 kilojoules. So this is what is the application of first law of thermodynamics. Now, what is the problem? What are the limitations of first law of thermodynamics? So the limitation is that though first law of thermodynamics gives us an energy balance, beyond that it does not tell us many things about the process. For example, it cannot predict whether the process is feasible or not. For example, if you are looking at a case where there is a heat transfer to a system, and if you want to find out whether this entire heat can be converted to work, in that case the first law would not be able to convey anything about it. The first law would be unable to tell whether the entire amount of heat can be converted to work. So the limitation is that the first law cannot predict whether the process is possible or not. The second limitation of the first law of thermodynamics is that it fails to talk about the direction of the process. It does not tell us in which direction the process would proceed. For example, the first law cannot tell us whether the heat can be transferred from cold body to hot body spontaneously. We know from common sense that a spontaneous heat transfer only happens from a hot body to cold body. And we know that this cannot happen from a cold body to hot body spontaneously. But the first law is not able to tell anything about it. Means if you ask the first law whether there can be a heat transfer from a cold body to hot body, the answer of the first law would be that no comments. Okay, so the meaning of no comments is that this is a limitation of first law. It is not, see, please note that the first law does not tell us that a particular direction process would happen. Means it would not say that yes, the heat transfer would happen from a cold body to hot body. It will simply say that I don't know the answer. Okay, so that is the meaning of limitations. Okay, so this you need to understand it very clearly, that limitations of the first law is the reason why we are defining the second law of thermodynamics. This limitations I have explained in the form of a schematic here. There is a schematic of heat engine. You look at it, this is a heat engine. A steam power plant is heat engine, you know. And this steam power plant, what is shown is the closed system wherein there are the energy transfers across the system boundary. For example, in the steam power plant, the heat is being supplied in the boiler and heat is rejected via the condenser. So the net heat transfer would be Q in minus Q out. Okay. Now, this heat engine is supplied heat equal to Q in, and there is some heat rejection Q out. It means that the entire amount of heat cannot be converted to work. Okay, so we cannot have an engine with the efficiency of 100% for this. But if you ask the first law whether an engine can have an efficiency of 100%, so the first law cannot comment on that. Okay, first law cannot say whether this engine would have an efficiency of 100% or 80% or 50%, whatever. What it will tell you is that, okay, so this is the system. So from the first law of thermodynamics, energy in is equal to energy out. So what is the energy in? So Q in plus W in is equal to energy out is W out plus Q out. So that is what the first law tells us. It does not tell you the conversion efficiency of heat to work. That is the limitation of first law of thermodynamics. So first law cannot tell whether an engine can have an efficiency of 100%. This is the limitation. Another example I had taken to clarify about the limitation of the first law of thermodynamics. So what you see here is a schematic of a refrigeration system where you have a compressor, a condenser, an expansion device, and an evaporator. Okay, so whether this system can be operated and we can produce cooling effect without supplying any work input to compressor. So if you ask the first law of thermodynamics, the first law of thermodynamics has no answer. Please note that it does not tell you that it is feasible. What it will tell you is that it cannot say whether this system can operate without any work input. Okay, so the first law of thermodynamics cannot tell us whether a refrigeration system can operate without consuming compressor work. Okay, that is a limitation of the first law. Okay, what it will tell us about the refrigeration system is it will tell us about the energy balance. For example, you know that in refrigeration system, heat is supplied in the evaporator and heat is rejected in the condenser, and work is supplied in the compressor. So this energy flows, you can energy in is equal to energy out is what the first law can tell us about the refrigeration system. It does not tell us whether this system can operate without work input or not. Okay, that is the point. So we need some other statements, okay, for answering the questions which the first law cannot tell. So one important statement of second law of thermodynamics is known as the Kelvin-Planck statement. So the Kelvin-Planck statement, if you look at the wordings of the statement, it is a negative statement in the sense that what it tells us is it tells us what is not possible. So it tells us that it is not possible to construct a device working on a thermodynamic cycle which produces work while exchanging heat with the single reservoir. So what is not possible? What is not possible? It is not possible to construct a cyclic device, a device which is working on a thermodynamic cycle. And how would be that device which is not possible? So it is not possible to construct a cyclic device which would produce work while exchanging heat with a single reservoir. You know that in thermodynamics, we define a reservoir as a source or a sink. Okay, so source is a reservoir which can give us infinite amount of heat without the reduction in temperature. And sink is such an imaginary reservoir which can absorb any amount of heat without increase in its temperature. So it is not possible to construct a device which is working on a thermodynamic cycle and it still produces work while exchanging heat with only a single reservoir. Okay, single reservoir means it cannot we cannot construct such a heat engine, okay, which would produce work which will exchange the heat with only single reservoir. right? So that is not possible according to Kelvin Planck. It means that what Kelvin Planck is saying, that we need at least two reservoirs if you want to construct a heat engine. Okay, and why for we require two reservoirs? We require two reservoirs because we need one reservoir to absorb the heat, to take in the heat, and other reservoir for the rejection of the heat. It means that the heat engine has to reject certain heat. In other words, what the Kelvin Planck statement is saying is that the heat. So once again, let me repeat this Kelvin Planck statement. The Kelvin Planck statement says that is a negative statement, in the sense that it tells us not what is not possible. So what is not possible? It is impossible to construct a device working on a thermodynamic cycle which produces work while exchanging heat with the single reservoir. In other words, we cannot construct a device which produces work while exchanging heat with the single reservoir. Means Q cannot be equal to W. Okay, this is a device which is getting heat from a single reservoir, that is a source, and it is converting the entire amount of heat to work. Okay, so such a device which is taking in heat and which is rejecting zero heat, okay, means it is converting the entire amount of heat to work, it is impossible to construct according to Kelvin Planck statement. Okay, so what is the efficiency of this impossible device? The efficiency of this impossible device is 100%. Okay, so we cannot construct a heat engine whose efficiency is 100%. Thermal efficiency is 100%. Such a device, such an engine is impossible to construct according to Kelvin Planck statement. Okay, so this is very interesting insight, and we'll discuss this again in much detail later. The second statement of the thermodynamics, second law of thermodynamics, is the Claudius statement. And what it tells us is, it is impossible to construct a device which is working on a thermodynamic cycle which has the sole effect. Sole means the only effect. And what is that only effect? Which has the only effect, the sole effect of transferring the heat from a lower temperature reservoir to a higher temperature reservoir. It means that, let me show you this. Okay, so this refrigeration system, what it does is, actually it is transferring the heat from a lower temperature reservoir, that is in the evaporator section. What it does is, it takes the heat from the space which is to be cooled. Okay, for example, in your household refrigerator, what does the evaporator do? It takes the heat from the freezer section of the domestic refrigerator, and it pumps the heat to the surrounding, which is outside of the refrigerator, okay, which is at the higher temperature, right? Surrounding is at higher temperature, and the freezer section is at a lower temperature. And the refrigerator, what it does, it takes the heat from a lower temperature, that is freezer section, and it pumps the heat to a atmosphere which is at higher temperature. And this system, we cannot operate without any work input. That is what the Claudius statement says. So what it is saying is that, essentially, it is impossible to construct a device which, while working on a thermodynamic cycle, transfers the heat from a lower temperature reservoir to a higher temperature reservoir without any work input. So the keywords are without any work input. So we can transfer the heat from a lower temperature reservoir to a higher temperature reservoir, but for that we need to supply some work. Okay, that is what the statement is. Okay, so the Claudius statement tells us that a refrigeration system is impossible if the compressor work is zero. So if you look at the limitations which we discussed, the limitations are addressed by the second law of thermodynamics. It tells us the direction of the process, and it talks about the conversion efficiency. Okay, so what we have learned in this lecture is two things. We have studied what were the limitations of the first law of thermodynamics. We said that the limitations of the first law of thermodynamics is, it does not talk about the direction of the process, and it does not talk about whether a process is possible or not. And we said that these limitations are addressed by the two statements of second law of thermodynamics. The first statement is the Kelvin Planck statement, which tells us that it is impossible to construct a heat engine whose efficiency is 100%, and the Claudius statement, which tells us that it is impossible to construct a refrigerator which does not have any work input. Okay, so now the point is, we know the two statements, we know the Kelvin Planck statement, we know the Claudius statement. What matters now is, how do we, as an engineer, benchmark the performance of the engine and refrigerator. For example, we now know from a Kelvin Planck statement that the engine cannot have an efficiency of 100%. So if the engine cannot have an efficiency of 100% according to Kelvin Planck statement, then what should be the ideal efficiency, what should be the ideal engine for designing? And that we need to study in the next lecture, which is the lecture on Carnot engine. Carnot engine is the engine which is having the maximum efficiency, not 100%. Mind well, it is the engine which is having the best efficiency. It is the best engine, and that becomes the benchmark for we engineers. Thank you very much.